All right, Trig. This is section 5.2, exponential functions. So we've been dealing with exponents in section 5.1, just like um, multiplying x squared times x to the third power and adding exponents together, or x squared cubed is x to the sixth power. Now, then your homework did things to you like fractional exponents, which was really, really difficult. But in section 5.1, we were just talking about combining x's, doing that stuff together. In 5.2, they introduce exponential functions, which is just a little bit different than exponents. We're talking mostly about things like y equals, let's say, 2 to the x power. In exponential functions, your exponent is your variable. It's not the other way around. You don't have like a numerical exponent and a base that is your variable. Here they're switched around, okay? And when you have exponential functions that look like this, they are going to be like exponential growth functions or exponential decay functions. The decay functions have to do with whether this number is greater than 1 or less than 1. If it's a number that's less than 1, it is a decay function, okay? And a lot of times you'll see a decay function in like half-life. So in half-life, it looks similar to like y equals 1/2 to the x power, where in year 1, it's going to be half of what it was in year 0. In year 2, it's half of that. In year 3, it's half of that. In year 4, it's half of that. So it's halving and halving and halving every single time. That's kind of resembles your half-life. So this is your decay function, this is your growth function. Things to remember about exponential functions is they will always cross at a positive 1 on the y-axis, because if I put 0 in for x, anything to the 0 power is always going to be 1. So it will always cross there unless I do any translations to it, which is what we're going to talk about next. So always crossing at 1, -1. Exponential functions I talk about, I think I've done in this class already, talking about a fart. And then here's your smell factor. So the smell is going down and down and down over time. And then you have your horizontal asymptote that is here. Okay, so that's an example of a decay function. Here you have exponential growth, which a lot of times population is represented with exponential growth because, people are multiplying exponentially. The population that's dying off is not dying off at a quick enough rate. We are actually growing faster than that. So exponential functions. So now that we know what they look like, exponential growth, exponential decay, we're going to talk about translations. So shifting them left, right, up, down, stretching them vertically, stretching them horizontally, that type of thing, okay? So you should have in a folder or something somewhere a sheet of paper that looks like this. And if you cannot find it, I don't know, we'll have to get you another copy somehow. But if you have this, go ahead and get this sheet out. We are going to fill in a column that I'm creating over here for exponential functions, all right? You may have some of these already filled in for like 2x plus 3, I think we've done together, maybe x squared we've done together, I don't know, but I'm going to create an exponential function. Exponential function y equals 2 to the x power. And we're going to see what happens to this function after I move him 6 units up, 5 units down, etc., etc. Okay, so if you need to pause this video while you grab this sheet, do that. Otherwise, we'll get you a copy of this tomorrow or sometime. So vertical translation, 6 units up. For a linear function, we're just adding 6 to the end of that. That is exactly the same as what we are doing here. We are taking 2 to the x power and then adding 6 to the end of it. 5 units down, 2 to the x, minus 5, that's it. Okay. When we're translating right and left, it looks a little different. Here we put it in parentheses. It's like right next to the x. So what it will look like in this function is x minus 9 up in the exponent. So the minus 9 will be up here rather than down below like the minus 5 was. If it helps you to put it in parentheses so that you can see that, that's fine. Okay. 4 units to the left will look like x plus 4. Okay. Again, these are the weird ones where you do the opposite sign. I think maybe I even had you star it. Opposite sign. So plus means right, or excuse me, plus means left, minus means right. So you use the opposite sign. Vertical stretch by a factor of 5. 5x is how it looks here. We're going to do 5 times 2 to the x power. 5 times 2 to the x power. Here, vertical compression by a factor of 1/3. 1/3 times 2 to the x power, like that. Okay. Horizontal stretch and compression. You should maybe have another star here that says like use the reciprocal. Okay, the reciprocal of stretching by a factor of 2 would be 1/2 like we did here. But it's up in the exponent. So this is 2 and then 1/2 x. Like that. Okay. Here, horizontal compression by a factor of 1/4. It's 2 and 4x in the exponent. If you need to put parentheses around it, go for it. Okay. Reflection over the x-axis. The whole thing is made negative, so you just put a negative out in front. And a reflection over the y-axis, just the x is negative, so you put an x in the, or negative in the exponent. Okay. So what does that stuff look like when it gets to like an exponential function? Obviously shifting up, down, left, right. If you shift this guy up, let's say 3 units, he's not going to cross at 1. He's going to cross up here at 4. But he's going to look exactly the same. So that's what he will look like. Left and right are going to be exactly the same thing. But vertically stretching and compressing, if you vertically stretch something, you're going to make him tall and skinny. So he's going to look maybe a little bit straighter up and be more of an L shape than a curvy shape. He's going to be kind of a sharp L turn. That's what a vertical stretch will look like. Okay. Vertical stretch will also look very similar to a horizontal compression. If I slam him this way, he's going to also be more of a sharp L shape. And then the same thing happens for vertical compression or horizontal stretch. If I horizontally stretch this guy, he's going to be a little bit flatter. Or vertically compress him, I'm compressing him this way, he's going to be a little bit flatter. Okay, so that's just kind of thinking about those in terms of the graph. In terms of the equation, it will follow these rules. Okay, so example 1 translations. If we're starting with 2 to the x power, they want to know what 2 to the x plus 3 will do. Let me zoom in. 2 to the x plus 3. This is just going to move him 3 units to the left, because plus means left. This guy, there's actually 2 things that are happening. 2 things, the -3 and the -4. And again, it matters what order you go in most of the time. All right, so -3 is going to happen first, because if I were to plug a number in for x, I would subtract 3 from it before I would subtract the 4, right? So -3, this is going to move him right 3, and then down 4. Right 3, then down 4, right? Horizontal stretches, example 2. We're starting with 3 to the x power this time. Okay, and they write this as 3 to the 0.2x. Okay, I don't like the way that that is written. I'm going to write that as 1/5 x, because 0.2 is the same thing as 1/5. Okay, 1/5 is in the exponent up here, and that is going to be a horizontal stretch by not 1/5, but 5, because you use the reciprocal. Okay. Down, and next one, 0.8. I write that as, let's see, 0.8 is 4/5, I think. And it's up in the exponent again, so that's going to be another horizontal one, but we have to decide whether it's going to be a stretch or compression. Okay, so my factor is going to be, I flip it by 5/4. So think about whether that's going to be a stretch or compression. If I'm multiplying by 5/4, that's a number that's bigger than 1, so I'm enlarging it. So it's going to be a stretch again. horizontal stretch. Okay. Negative x in the exponent, we went over that rule. That is reflection over the y-axis. Yeah, reflection over the y-axis. Okay. And then this last one, oh, I'm all the way up there. This last one has two things happening. 1, 2. So I'm going to write this again as negative 4 is 2/5 x. Okay, so let's worry about the 2/5 first. Since he's in the exponent there, he is going to be a horizontal something. I'll do horizontal something. Horizontal something by, flip it, is 5/2. Is that a stretch or compression? 5/2 is bigger than 1, so horizontal stretch by 5/2. And the negative is reflection over the y-axis. So those are two different things. Okay. A lot of people think that negative 2/5 goes together, but it's actually two separate pieces. Okay. All right. Next page. Done with that. Simplifying expressions with rational exponents. Oh no, they do want us to do more. One more describing the transformation. Okay, so the graph of 3 to the negative 0.4x is shown below, or right here. They want to know, without graphing, describe the transformation. Okay, so this guy, basically they're saying what's being done to him, right? Now pay very close attention to what they say your function is starting with. We are not starting with 3 to the x power, so we don't have to tell you, or I don't have to tell you, what the negative, what the 0.4 is doing. I only have to show you what's different from here to here. And the only thing that's different is it's being multiplied by 4 out in front. That is going to be a vertical stretch by 4. If I'm starting with this function, the only thing that's being done to it is the 4. So vertical stretch by 4, and that's it. Okay. From this guy to this guy, I have a negative 2 out in front, which actually is two separate things, the negative and the 2. So let's do the 2 first. The 2 is going to be a vertical stretch by 2. And the negative out in front is going to be a reflection over the x-axis. Reflection over the x-axis. Okay, so two separate things. There's that. All right, now let's get into some of these problems here. All right, and I'm not going to be able to give you the answer to these because I don't have my calculator with me, but I'll show you how to set these up, and I want you to plug them into your calculator and get an answer. So you invest $5,000 into a stock that is increasing at a value rate of 3% per year. What that's going to look like is this equation. This is your initial investment. They do 1.03 because you're taking that 3% and you're adding it back to what you were originally have. So this is like 103% of the original, adding it back to the original. And I'm doing that over X number of years. So assuming that the value of your stock growth or continues to grow at this rate, how much will your investment be worth in 4 years? Okay, all I'm doing is plugging 4 in. So you plug that in and get an answer. All of these part B's, we're going to wait to do when I come back on Thursday. Okay, when will your investment be worth $8,000? Okay, we can look on the graph to see when that will happen, but I'm going to show you a trick involving logarithms in order to do that. Okay, so we're going to save the part B's until I come back. So what I'm going to have you do is just worry about plugging these in. All right. So example 5, based on the data from the past 50 years, the world population in billions can be approximated by this function, where x equals 0 corresponds to 1950. That's important. Make sure you take note of that anytime they do that. 1950 is year 0. They want to know what the population is in 2015. So I'm not going to plug 2015 in for x if x equals 0 corresponds to 1950. I'm going to plug in 65, I think. 2015 minus 1950 is 65. So in your calculator, plug this in. 1.0185 to the 65th power and get an answer. All right? And what year will the population double? We're going to save that for Thursday or tomorrow. Okay? We'll do those together. So figure out what this guy is in your calculator. Okay, a couple more. the amount from 1 kilogram of plutonium that remains X years after X years can be approximated by this function. Okay, plutonium is going to it's like radiation. Plutonium is going to decay after after a certain period of time. So estimate the amount of plutonium remaining after 10,000 years. This is another one you're just going to plug in. 10,000. So plug that in, get an answer, go. All right. All right, last little bit, last little pieces here. Population growth. If the population in the United States continues to grow, as it has since 1980, then approximate the population in millions, where t equals 0 corresponds to the year 1980. This is the function for population, right? So t equals 0 corresponds to 1980. Estimate the population in 2015. So 2015 minus 1980 is 35 years. So again, this is another one. Just plug it in. E to the 0.0093 times 35. Practice plugging that into your calculator, see if you can get an answer. You have an E button in your calculator. Okay, find it. It's next to the button that says LOG. We'll learn what a log is later. But plug E into your calculator, get an answer for that. I'll explain to you what E means later. It's a constant. It's this number right here. It's kind of like pi. It's a decimal number that goes on forever. We'll talk more about him later. Save part B. Okay. And the last thing, the population of fish in a certain lake at time t months is given by the function blah, blah, blah. There's an upper limit on the fish population due to the oxygen supply, available food, etc. Graph this function and find the upper limit of fish on a population. I think I'm going to go ahead and save this one also for when I come back. We'll talk about logistic models. Logistic models are a lot of times a lot better than exponential models, because if we use an exponential model to represent population, okay, exponential growth is going to keep going up and up and up and up and up forever and ever and ever and ever and ever, and it's never going to stop, okay? But realistically, our population is not going to continue to increase, because for one, we're going to run out of space on Earth and we're going to have to start living on Mars, and for two, we're going to run out of food to feed these people, so we're eventually all going to die off, kind of like bacteria do in a petri dish. Eventually, when they run out of food, all the bacteria dies. So a logistic model is a lot better, because what happens in a logistic model, and we'll graph this when I come back, this exact one, but when in a logistic model, it goes up and it goes up and it goes up, and then it levels off at a certain point, because your population cannot go any higher than that. So logistic models are wonderful things. We'll talk about them later. We haven't really talked about them in any other math class before, so yay. We'll graph that later. So start working on the homework. You won't be able to do anything like these part B's, but at least do the ones where you have to plug in and describe the transformations. Okay.